All right, so just to wrap it back in, what I have written here about the semester, I will officially put some stuff on Canvas to let you all know how we're going to go forward. None of you are going to get a bad, well, I shouldn't say a bad grade, but none of you are flunking, so that's good. All right, so here's where we left off. So if you paid attention last time we met, which was last Wednesday, right? Yeah. So last class we did the following. We stated a bunch of definitions. Of some terms that probably seemed, they almost probably seemed out of place. You know, we talked about these things like a closed curve, a simple curve. We talked about this idea of a conservative vector field. And then we kind of, it almost seemed like we just jumped ship. We just started doing this thing called the fundamental theorem of line integrals, if you remember. So we stated a bunch of definitions and quote unquote proved what's called the fundamental theorem of line integrals, or for line integrals. So let's remind ourselves what this formula, excuse me, is saying. It says the following. It says that in some situations, a line integral, which of a vector field, which we know looks like this, can be reduced to the following computation. So when is this true? Well, it's true when f is equal to the gradient of phi and R is a parametrization of C. So the calculation we did was kind of interesting. We said, okay, if you look at the last lecture, we said, is there some sort of analogy to the fundamental theorem of calculus that was studied way back in Calculus 1 and used excessively since then? And what we came up with is we came up with this analogy that if the vector field was the gradient of some scalar field, or what we call a scalar function, phi, then we have this simple formula. And so the question that we left you with is, so the big question would be, how do you use it? If you think about how you use the regular fundamental theorem of calculus, in order to use it, you had to know what the antiderivative of your integrand was. And that means whatever function you wanted to integrate, if you wanted to use that shortcut we learned, you needed to know its antiderivative. And we spent a lot of time learning tricks of doing that. We spent time in Calc 1 with like the substitution method, and in Calc 2 you learn all these tricks like integration by parts and all these algebraic and trigonometric tricks. So the question is, how do you do that in this scenario? So how do we use this? Well, the question then becomes, given f how to determine phi if it exists. So this is the question. If we want to use this tool, we have to know how to set the problem up so that we can use it. Okay. Anybody have a question, comment about this?
Do you have to wear masks to get your rock star?
Yeah. You know, it's funny. They're on sale now, Giant Eagle, 3 for $5. My rock stars. It's my one vice. How about last week? What class? It was Calc 2, I think. Maybe Calc 1. My youngest comes down with a beer. She's trying to give me a beer. It was pretty funny. No beer before dark, Ricky. That's the rule. Okay, so, oh my God. Got emails galore. It's absolutely impossible to keep up with emails during the pandemic. All right. So we need a definition. So if f equals the gradient of some phi, what we do is we call phi a potential function. So now, if there's two ways to say this statement. You could say f is conservative, or you could say phi is a potential function for f. It's sort of like the thing O'Grady is older than Matt. Matthew is younger than O'Grady. Two ways to say the same fact. All right, so we're not going to prove this theorem. But there is a very nice theorem that tells you when you can find potential functions. So that's what we're going to talk about now. So the question, when does phi exist? Well, here's the theorem. So there's two cases to consider. We have to consider a vector field in R2 and a vector field in R3. But we can kill both of those birds with the same stone, because in the case of R2, you can just set the third components to 0, and that will reduce the problem down. So here's where all those technical terms we defined last week come into play. So let's remember, F has components. We've been calling them F, G, and H. So capital F is a vector field. It takes an input of 3 numbers and associates it or maps it to a vector in 3 dimensions, or a point in R3, if you will. So let this be defined on a connected and simply connected domain in R3. So as long as the domain is connected and simply connected, And then you need this other technicality. You need its first order partials to be continuous. So we need this requirement to be true. We need all these fancy terms. And to be honest, in Calc 3, we're not going to give you a scenario where they're not. Bad things happen if these things aren't assumed to be true. Okay, now here's the statement. Then f is conservative, or f equals some gradient of a scalar field if and only if the following is true. The partial of f with y is equal to the partial of g of x. The partial of f with respect to z is equal to the partial with h with respect to x. And then partial of g with respect to z is the partial of h with respect to y. Okay, so this is really only a partial solution because this just tells us when it's there. It tells us it exists. It doesn't tell us how to find it. So let's make a note. For f in R2, only this guy matters. The other two disappear, right? Because there would be no h component. H would be 0, right? The third component doesn't exist in the plane. All right, so what we're going to do is we're going to do an example which is really the epitome of what I call deductive reasoning. We're going to give you a vector field. We're going to say, okay, it's conservative by this theorem. And then what we'd like to do is we'd like to figure out, determine the phi. See, it's real easy to go one way. If I give you a phi, you just take its gradient, and now you have a vector field. There's nothing interesting about that. We've been computing gradients for months. But the other way is the more interesting direction. That is, if I give you a vector field f, can you find a potential function? Well, first off, you can't go looking for it if it doesn't exist. So the first thing you do is you use this theorem and say, okay, it exists. And then once it exists, then you have to use your deductive reasoning skills to figure out what in the world this phi is. And why do I say deductive reasoning skills? Because it's not like some procedure like you learn in Calc 1 where you, hey, let's just differentiate it and differentiate again. You have to really use some reasoning here. All right, so let's do two examples. We'll do an example in R2 and we'll do an example in R3. And then we'll move on and then let you suffer with doing it. later on. Okay. Does anybody have a comment or a question? So here we go. So given F, oh my God, what is happening upstairs? It's like a, ooh, Amy's getting mean. So here we go. Let's take this vector field. What is happening up there? It's like someone's, I think one kid's killing the other kid. All right, so here we go. What would I do if I lived in like an apartment? I wouldn't be able to do this. I'd have to like tie up the wife and kids or like kick them out in the weather. My house sounds like it's going to collapse. All right, so here's our function f. We want to know if it's the gradient of something. Now, of course, you could say, let's just guess and check. And maybe if you're sophisticated with a computer, you can write some algorithm that guesses and checks real rapidly until it guesses correctly. But that's not how we want to play this. We would like to actually, reason what this creature is going to be. All right, so so here's what I'm going to do, and this is sort of how you have to think about this. Let's call this the solution. So I'm going to call f of xy this piece. Oh, excuse me. And call g the second piece. F's the first component, g is the second component. And then what I'm going to do is I'm going to appeal to that previous theorem. What did the previous theorem say? If you go back, it says that you need to study the partial of f with respect to y and the partial of g with respect to x. And so f with respect to y is negative x, and g with respect to x is x. So what does this mean? Well, according to our theorem, there is no potential function. There is no potential function because these partials aren't the same. Does that make sense? So there's no, you could spend the rest of your life looking for a function whose gradient is this vector field, and you're never going to find it. So again, if we would have started trying to look for that thing, that would have been a bad idea because, well, frankly, it's not there. All right. Does anybody have a question about this particular guy? So let's finish the problem off like a fancy, smart mathematician would, or a physicist or engineer. So what we can conclude is f is not conservative. Well, I shouldn't have ran so fast from that. Does anybody want to ask a question about it? Okay. Let's go to the next example. All right, so now take f to be about e to the x cos y, comma, negative e to the x sine y. So let's word this problem. Let's verify this guy is conservative and determine the potential function. So we're kind of phrasing this one a little differently. So once again, I'm going to set f equal. I'm going to stop writing the independent variables when the context is clear, just because it saves us space. So we know g is a function of x and y, and f is a function of x and y. So the partial of f with respect to y is negative e to the x sine y. And the partial of g, excuse me, say what you mean and mean what you say, Brady. The partial of g with respect to x is minus e to the, why did I put a minus sign here? Losing my mind. Check that. I had a typo there, guys. This is just e to the x. The minus sign's actually out front. So if you take these derivatives, this implies f is conservative. Okay, so we know it's out there. Now we just have to put the puzzle together. And you know, just like you guys build puzzles. I mean, I'm sure you guys at one point in your life have put a puzzle together. Everybody has their strategy of how they do it. And my kids, I've been trying to teach them, get all the edges first, separate them, and then put the edges together. You know, there's a strategy to these things. Every calculus book that you read will give you a strategy to finding potential functions, and they will all be very similar. As you guys know, I ain't about memorizing formulas. I am not about memorizing procedures. I'm about thinking. I'm about doing. And when you think and do things enough, they become natural to you. And so, as I've always said to you, I want you guys to do things to an extent that they become natural. You know, just like driving a car is natural. You don't think about certain things. When you walk, you don't think about certain things. Well, maybe sometimes you do if you're walking down the street, but get the point I'm making. You want things to become natural. And I think the best way for this stuff to become natural is to just do it and not try to follow a specific procedure, but to reason your way through the argument. So here's how I would encourage you to think about it. I keep writing my fees like drunk peas, and that's not good. I would fail Greek class. So to get phi, recall, what does it mean? If I tell you that f is equal to the gradient of phi, let's write that out in details. That means that f, what is f? Well, f is Rf, comma g. And what's the gradient of phi? Well, that's the partial with respect to x, comma, the partial with respect to y. Now write out what is f. We know what little f is. We wrote it on the previous page. That's e to the x cos y. And then g was minus e to the x sine y. So what you have is I have an equation. The right-hand side is the unknown. In particular, there's two unknowns. I'm missing two functions. I'm missing phi of x and I'm missing phi of y. So really, this is now an exercise in differential equations, right? Think back to Calculus 2. We studied these things called differential equations. I have two equations, and the unknown in both of them is the same. I'm trying to find phi. And what I know about phi is I know two facts about it. I know what its partial with x looks like, and I know what its partial with y looks like. So in order to find phi, I might reason, why don't I undo these derivatives? So let's do that. So here's what I'm going to tell you to do. So I want to investigate phi of x equals e to the x cosine of y. How am I going to investigate? I am going to integrate. Now, there are two variables to which I can integrate. So what I'd like to do is, if I can kill that partial with respect to x, I get information. So what I'm going to do is I'm going to integrate out x. So if I do that, the left-hand side, if I just integrate x, I get phi. And on the right-hand side, it's the integral e to the x cosine y dx. Now, what is the integral of e to the x? We know the integral of e to the x is just e to the x. So now we're going to do some reasoning, and it might take a moment for you to quite understand what this reasoning is. If I integrate, remember, we know that our function phi is a function of x and y. When we integrate e to the x, so let's write it like this. Let's pull out the cosine y, because that's not needed in there. And so now the integral of e to the x is just e to the x, but don't forget I have an arbitrary constant. Now, the thing about this constant is it might not just be a number. Lydia, calm down, please. No respect for learning, Lydia, I'll tell you. So look, so let's think about this equation. Think about this equation. C doesn't necessarily have to be a number. C could actually depend on Y. Now hear me out again. If you're confused by why I'm saying C could depend on Y, look at this relationship. If you take the partial of this thing on the right-hand side with respect to X, if that C, which depends on Y possibly, does have a Y, its partial is still 0. Differentiate this. Differentiate now with respect to X, and you get phi of X is equal to cosine Y e to the X. So let's make let me kind of corner off something. I want you to understand what I mean by this. So you can check what I'm saying. If you take the partial with respect to X of phi, let's think about what this means by definition. That's the partial with respect to X of cos Y e to the X plus cy. Well, this just becomes cos Y e to the X plus 0, which of course is just F. As expected. So again, it might take a moment for you to understand why I have this cy here. Does anybody have a question? Okay, so I'm starting to discover what phi looks like. Phi is cosine Y e to the X plus something. And this something might have Y in it. So now what I'm going to do is I'm going to take my new guess of what phi is and now differentiate it not with respect to X, but differentiate it with respect to Y. So hold on to your hats now. This stuff is super fun. So now differentiate with respect to Y. So I'm going to take my phi of xy, which we know is equal to e to the x cos y, plus c of y. What does this become? Well, this is now the partial with respect to y equals minus e to the x sine y plus c prime of y. Now, here's the interesting thing. We know what e to the x sine of y is. This is actually equal to, if you remember, g. This is our g. But what else is equal to g? This is also g. So the only conclusion then, sorry, it's all right, it's okay. It's funny, I understand. All right, wow, what'd they do? You leaving? All right, have fun. All right. We know we're joking. You guys know we're joking, right? Yeah, they know. They know. Amy, they don't think that. We're having fun. All right, so what is the only conclusion? Well, if you subtract it from both sides, The only conclusion is that C prime, her car seat's in my car. See ya. Is that C prime is 0. So in fact, C is just a number. Turns out it wasn't dependent on Y. It was just a number, if anything. Well, let me go back because you might have a question. Does anybody have a question, comment? I would highly recommend you work through this again. Make sure you're picking up some of the reasoning. Comments, questions? All right, so what we can conclude is the following. We conclude that the potential function is just e to the x cosine y. So this one, if you want it, you could do a plus c, but it's unnecessary. All we are looking for is one potential function. We don't care. So maybe you want to make a note of that. So maybe we set this for convenience. That way you don't have to write. But don't forget, you can add a number to that, and it would definitely work out. Does anybody have a question? As you would imagine, if it's a vector field in R3, it's even more tedious. Because you have 3 partials to undo instead of 2. Does anybody have a question? Very wild it is, very wild. Okay, so how do you get good at this or even average at it? You do it. You do them again and again. You got to practice. Now, one of the concerns you might have is you might say, okay, what are we doing all this for again anyhow? Well, we could study, there's lots of interesting reasons to study conservative vector fields. We motivated their importance by saying that if a vector field is conservative, its line integral could be easily calculated. And then the counter argument you would have is, well, how can you say it's easier calculated if we'd have to spend all this time finding phi? And so, yeah, I agree with you, but But again, we wouldn't be so interested in learning about this stuff if it didn't have its uses. The fact of the matter is, many of these things that we're attempting to calculate are often quite difficult to calculate. And so anytime we might be able to obtain a shortcut, so to speak, or an easier calculation, that's what we're looking for. So, you know, I'm not going to sit here and pretend that that this stuff is easy. These calculations are often tedious. The good news is software is getting better and better at doing them for us. So as long as you understand what's happening, you have technology to do lots of the computation for you. Okay. So here's a cool fact about conservative vector fields. So theorem, if f is conservative, conservative. Quarantine got me smelling all kinds of craziness. So if f is conservative, and we have to put these technicalities on an open, connected domain. Here's a cool fact. Then the integral, the line integral f dot t ds is 0 for all closed C. I guess I should be very careful here because it has to be simple as well. So this is a very useful fact, particularly when you're dealing with applications, things like flux and circulation. And by the way, it's useful to show you a piece of so I'm going to add something here. This is sort of standard notation. One of the ways we let the reader know that an integral is over a closed curve, you know, like a circle, is we put that little circle on the integral. So let's make sure everybody's cool with that. So note, so if C is closed, we often write this instead of this. So there's that little added circle. Some nerds, believe it or not, actually even put like a little arrow around it. Now, we haven't mentioned much about this concept of orientation, and we're going to soon enough, but I've often told you the reason we stick with these parametric representations of curves is they give us a direction. We always want to imagine that we're moving along a curve. so if I have a circle, just take a simple curve like a circle. If you're traveling around a circle, you can go clockwise or you can go counterclockwise. So we haven't stressed this yet. But orientation, direction matters. So what do I mean by that? I mean the following. Now I'm going to ask you to do this because I've done it enough in my life. So how do we illustrate to you that direction matters? Well, hopefully you understand that intuitively, you know, from the concept of what we talked about, like flux and work. But you would imagine if you're running outside and the wind is behind you, it's going to be a little easier to run than if you're running into the wind. I think you all agree with that. Just like if you're in the river swimming against the current is a little more difficult than swimming with the current. So direction matters. And so to illustrate that even in an arbitrary sense, what I'd like you to compute is the following. Compute I think I gave you this on the last homework. I'm not positive if I did. I think I did. So compute this. Pick any example. I don't care which one you pick. Pick a simple f. Pick whatever. You can even just do it in R2. So we'll call this C1. And then take the same exact parametrization, but instead of starting from A to B, let T go from B to A. So here's a good example. So the only difference is the direction traveled. So if I were to sort of call this C, this direction is C1, and then C2 would be coming the other direction. Now, the only way this is going to make sense to you is if you pick specific examples. What's a very simple curve to pick? Why don't you pick like a circle? And then pick a simple f, like 1, 1, or pick anything. Just pick a very simple thing, and I'll work with these things. Get an idea, the intuition for what's happening. Because since direction matters, we all are going to have to agree on which direction do we want to call sort of positive versus negative, or forwards versus backwards. So to help illustrate, imagine traveling around a circle. Do we all want to agree that clockwise is positive and counterclockwise is negative? What do we agree on? And we do this in other, we've done this since we started graphing in algebra class. We all agree that up and down is the y-axis. Positive is up, negative is down. We all agree that left and right is the x-axis, and when we go left, that's negative, and when we go right, that's positive. We all agreed on that. When we drive cars in the United States, we all agree to drive on this side of the road. We have these conventions, and there's no difference here. When we're doing line integrals, more specifically what we call oriented line integrals, direction matters. And if you want some intuition for it, just like I said, imagine trying to swim across the river. Current is going to affect how difficult it is and where you end up on the other side. Does anybody have a question about this? To stimulate your mind a little more before we leave, I keep using this word oriented because we're going to hear a lot more of it in the coming classes. What we're now going to generalize these ideas. So let's take a moment to think about where we're headed. Where we're headed is the following. We've now sort of found this analog for the fundamental theorem of calculus for curves. Or if you'd like to, you could say for vector fields. And so the question we might ask is, okay, what other kind of integrals are there out there? What other analogies are there? So if you think about the path we've taken, we studied curves, and now we reduce these new types of integrals along curves to ordinary integrals. And so if you ponder this, you might say, okay, well, what other integrals are out there? Well, we had these double and triple integrals. And if you start thinking about integration and how it's comparing to derivatives at the boundaries of things, that's what we just saw. You might think that, okay, maybe the integral of a curve is somehow related to the region inside. Or maybe the integral of some surface. Maybe like, let's imagine we have a sphere. Maybe if we integrate on the surface of that sphere, that's somehow related to what's inside that sphere. Now that might seem completely out of nowhere that I'm saying this, but it's not if you think of the analogies with what we've been doing. The only thing we'd have to do then is we have to somehow describe what does it mean to integrate a surface. And then if we have a notion of that makes sense and has sort of physical applications or intuition, which it will. I mean, imagine, take a sphere, think of it as a cell. You have positive and negative, say you have charge inside and outside, and you want to measure the charge difference. We call that potential difference. One of the ways in which we do that is through integration. And again, I've used the word flux before. So this notion of expanding what we can integrate, that's our next sort of step. And it turns out we have to sort of, I don't want to say invent, but we have to talk about even new types of derivatives. Sort of these generalizations of the derivative to help us sort of formulate these integrals and how we're going to compute them. So that's sort of our next path down the road. What can we integrate next, and how do we do it? Sounds like fun, huh? So let me say this one more time before I end. What we've just seen is we've seen that in Calculus 1, the integral, if you want to think about it, depends only on the values at the endpoint of the interval you're integrating over. What we saw with the line integrals is there's a way to show that a line integral is only dependent on the value of the potential function at the endpoints of the curve. That's what we saw. So if that analogy is going to be true, that would make us believe that if I wanted to integrate over a region in the plane, say like a circle, or if I wanted to integrate over a square or any region in the plane, those analogies suggest that somehow those double integrals that we studied before can somehow be related to a value along the boundary of those regions. And then if we go up another dimension, we might think that there's even more is true. Take some object in R3, take a sphere, as I said. Or take a cube in 3 dimensions, or any solid in 3 dimensions, and suppose we want to integrate over that. Those were triple integrals. And so these analogies that we're building suggest that maybe a triple integral can be related to something on the boundary of that surface. It turns out it's going to be the case, but we have to build up the machinery for this. So the last thing I'll leave you with before we go is the following, because this is going to be real fun on Wednesday. It's one of the most important things, and you can start reading about it. So on Wednesday, so we do this in more depth. With regions in R2. And so if you're looking ahead, it's called Green's theorem. So Green's theorem is going to relate double integrals to line integrals. And what that does is that relates something to its boundary, as we've now seen a couple times. So anyhow, you guys have any questions, let me know. And on Wednesday, that's what we'll do. It will be super fun. It will be maybe overwhelming, because it always is. Such is life, though. Does anybody have a question, comment? All right, I'm going to stop recording.